So, in this lesson we will look at types of hydropower turbines used in small hydropower projects. So, large hydropower projects usually have conventional types like Pelton and Francis where we are going to look at, but there are other versions that are preferred in small hydropower projects. We will look at all possibilities. So, the function of the turbine is to convert the kinetic energy in water jet to kinetic energy in the turbine and impart it to the generator. So, the potential energy in the water at the high altitude will be converted to kinetic energy and which will be imparted to the turbine, and then from the turbine shaft it will be transferred to the generator, and then the generator will be converting it to electricity, and that is the energy conversion part. So, there are many types of hydro turbines used in small hydropower plants. The type of the turbine for a particular project depends on the head and the rated flow of the project. So, which we now know how to determine. The expected turbine speed is also a consideration, because usually turbines work at lower speeds. So, the lower speed turbines is a problem, because then you need lower speed generators which are multipole. So, multipole turbines with salient pole type are expensive and therefore, it is a consideration. Thus, different turbines are produced for high head, medium head and low head projects. Depending upon the way the water enters and imparts energy into the turbine, they are further categorized as impulse turbines and reaction turbines. Two major types of hydro turbines are impulse turbines and reaction turbines. So, in an impulse turbine, water jet hits the turbine bucket and passes away from the turbine. The runner of the turbine is inside a chamber containing air at atmospheric pressure. So, in an impulse turbine, there are number of impulse turbines, but the turbine runner is in air, right. It is not immersed in water. Therefore, water hits the blade and passes through and go to the rail race. Reaction time turbines are completely immersed in high pressure water. Then the water comes and pushes the rotor and goes away. The kinetic energy of the water is imparted to the turbine runner when water goes through the turbine blades as per the Bernoulli principle. I think you know the Bernoulli principle, where the aeroplanes also work, because one surface is longer, other surface is shorter. Therefore, when the fluid flow is there, there will be an additional force because of the vacuum effect. So, that the same principle is used in these reaction turbine blade configurations, so that the force can be created for the rotation. Impulse turbines such as Pelton, Turgo, cross flow and reaction turbines such as Francis, Kaplan are commonly used in small hydropower plants. So, we will now look at some characteristics of and the types of impulse turbines. Impulse turbines are very popular in small hydropower plants due to variety of reasons: ease and cost effectiveness in fabrication, less vulnerability to sand and other particles that may enter the turbine in operation, high part load efficiency are some of them. Pelton, Turgo and cross flow are some of the famous impulse turbines used in small hydropower industry. So, you know that normally in any country or any region, when they start the construction or implementation of small hydropower projects, normally they start with high head project opportunities, because they are more cost effective, easier to construct, smaller in size, because the amount of water you have to handle is smaller, Q is small, H is large. High head projects, they are easier to implement. So, once you have exhausted with high head project, you will go to medium head projects, and then if once the medium head projects are also done, you will go to low head project. That is the normal sequence. But of course, there can be here and there differences because of the opportunities and other available situations, but this is a normal way. Therefore, impulse turbines and high head projects are normally preferred in small hydropower industry. So, Pelton turbine is the king of high head turbines. So, in large projects or small projects, Pelton is a very proven old technology, and very efficient, and also the technology has been improved in construction of that. The runner of the Pelton turbine has a set of buckets connected to a steel wheel. The high pressure water coming through the nozzle in case of a single jet or several nozzles in case of multi-jet hits the turbine buckets and imparts the kinetic energy in water to the rotating kinetic energy in the turbine runner. You can see the typical turbine Pelton turbine here, right. You can see the buckets. So, the water jet comes and hits this middle portion, middle ridge, right, and then water goes to the two sides and goes away, right, goes away. And this is, that this construction is monolithic, that is, this entire thing is cast in as a single piece, and then the blades are machined, right. Therefore, it is lot of machining and labor work, because you can't do completely by full machines here, right. People's intervention is required because of the complicated shape, and therefore, the balancing and identical these buckets have to be identical, and finally, the entire thing should be fully balanced. Otherwise, what will happen? Otherwise, vibrations will result in when it is rotated. Therefore, it is imperative that the full wheel is balanced, right. So, because of all these things, Pelton wheel is a bit expensive to build, and it has to be very sophisticated technology in machining process. There have been efforts to make these buckets separately, and then either to bolt or weld to the rim, right. But that has not been very successful, because of the that when the water hits bucket, full stress goes to the stem, right, and next moment it is released. Therefore, the bucket stem undergoes lot of stress and release, right. So, that causes failures, we will come to it again, right, when we see some more details here. Here you can see this is the nozzle that I talked about, needle valve I talked about in previously, right. So, this is the needle, this goes up and down, right, opening and closing the jet. So, when you want to reduce the generation, you just simply insert a little bit, so that the Q of the rate of flow rate of the jet will be reduced, right. So, that is how that in a run of river scheme, we will come to this later in a later discussion also. In a run of river scheme, water coming into the project can vary slowly during the day. If a rain comes, slowly the flow rate goes up, then the flow level at the water level at the forebay tank tries to go up, which will be sensed, and the signal will be sent to the needle valve, open a little, right, open a little. Then again water consumption or the flow rate will increase, and thereby the forebay tank water level will come down. We will discuss that in a different place in detail. Here you can see the water coming through the nozzle after hitting the buckets reflects back with an angle of 165 degrees to avoid interference with the incoming water jet, right. So, water comes here, goes out, right, with 165 degrees deflection, and then goes out without hitting the incoming water jet, right, incoming water jet. So, you can see about 93% of energy is imparted, balance goes with the water, right, balance goes with the outgoing water, right. Pelton turbines can be installed with its axis either vertically or horizontally. However, the horizontal axis Pelton turbines are more common in small hydropower plants, whereas the vertical axis configuration is common in large hydros. So, I told earlier also, large hydros, the weight of the generator and the turbine are excessive. Therefore, if you have horizontal axis might deflect, due to the weight, and therefore, it is a problem. Therefore, they prefer the vertical axis configuration with a thrust bearing at the bottom, right. And here you can see the physically constructed nozzle, right. Here the nozzle part you can see. Now, this is fully closed, right, this is fully closed. So, it has to be taken out, this is a dismantled state. So, it is in the fully closed state. So, it will go back when you want to open the nozzle, right, open the nozzle. The problem with the welding or bolting is the you know that fatigue failure, right, fatigue failure. I think you have heard about fatigue failure. When you take a steel wire and bend couple of times, it breaks. That is due to the fatigue failure, right. Several times you bend it, it breaks. They are the same way when these buckets are subjected to constant regular stress at the bottom, at the stem here, right. So, it gets fatigue failures, right, fatigue failures. So, after some time cracks develop, and when one bucket breaks, it can go around and hit the other buckets and destroy the entire system, entire wheel, Pelton wheel, right, if the one bucket breaks. So, it has happened. So, for very small, so I visited before buying equipment some Austrian companies and German companies. They make very small, maybe 50 kilowatt like small plants, still with buckets separately made and welded or bolted. But for large machines above say 200 kilowatt and above, they always cast one piece and then carve the or machine the buckets, right, machine the buckets separately. Here I think we discussed this as elsewhere as a answer to a question. Here are some typical efficiency curves of hydro turbines, right, efficiency curves. You can see the Pelton is having the very good part load efficiencies, right. So, this is the percentage Q, right, percentage. This is efficiency in percentage, right. So, you can see the Pelton turbines have very good efficiencies, right, very good efficiencies. For large hydro, it can go even little above, and then you can see Kaplan has the second better efficiency. Kaplan machines we will discuss in a little while, and then the Francis, right, has some poor part load efficiency. If it is 30%, efficiency will be 70%, whereas in Francis it can be Pelton it is 80%, right, and other cross flow and propeller type machines, they have very poor part load efficiencies. So, the Pelton turbines operate with a high efficiency over wide range of flow rates. Therefore, for power plants with a wide variation in the flow rates during the year, if other parameters permits, Pelton turbines are preferred. Pelton turbines are preferred to be manufactured from a single monolithic alloy steel casting. The buckets have to be carved into the casting and involves a challenging skill job. The involvement of machining is limited and work is labor intensive. To reduce the cost of manufacturing, efforts have been taken to manufacture buckets separately and either to bolt or weld them to the wheel. However, fatigue failures have been recorded in many such instances, and therefore, unless for very small turbines, monolithic construction is used. So, these things I explained earlier. So, Pelton wheels therefore are cast in single piece and then carved into the buckets are carved into it. The turbo turbine, probably you may have not very much heard. So, it is a variant of Pelton, right. It is also impulse turbine. So, I have put a turbine here. So, if for one of our projects we use turbo turbines, this 2.5 megawatt machine power plant, we put 1.25 into 2 turbo machines, right. So, they have been working now last 20 years, no issues, right. That is, but these turbines are relatively little smaller for the same capacity and also cheaper. So, price was the main factor why we selected this turbine, turbo turbine, right. So, we can see here. So, this is where the water enters, right, and jet is here, and it goes from inside from this side and comes out from this side, this other side, right here, like here. So, the needle valve and that system is the same as Pelton, water jet and control, everything is same, but now how it enters the wheel is different. It enters from one side and goes out from other side, right, imparting energy. Like the Pelton turbine, turbo is also an impulse turbine. The technology was developed relatively late by a British manufacturer, but today there are several manufacturers of turbo turbines. In a turbo turbine, the water jet coming from a nozzle enters the turbine from one side and exit from the other. Therefore, there is no chance that the exit water hitting the incoming water jet, and therefore, there is no necessity to control the incoming water jet on this account. Right. So, these are advantages, but their efficiencies also run into the similar levels. You can see not the turbo turbine is not here. Turbo turbine is almost like Pelton turbine, right, almost like Pelton turbine. So, you can consider for turbo also the same efficiency curve. So, for the same capacity, the diameter of the turbo runner is smaller than the diameter of the same Pelton runner and therefore cheaper. Moreover, the turbo runner obtains faster rotating speeds and therefore easier to connect to a generator of the higher speed. Similar to the Pelton turbine, turbo also has good efficiency over wide range of flow rates. Therefore, for small hydro projects with wide flow variations throughout the year, turbo turbine is also a good application. Turbo turbines can also be installed with either the axis in horizontal or vertical position. Manufacturing of turbo turbines is more difficult compared to a Pelton turbine, and the buckets of a turbo turbine is more fragile. However, being smaller in size, turbo turbine is cheaper compared to a same size Pelton turbine. You can see this shape, you can see these are not very thick. Therefore, if something hits it, it will easily split, right, not like Pelton is Pelton buckets are more stronger, right, but turbo buckets are thinner, right, and can be damaged easily. So, therefore, we have to take care of any strange objects coming in and hitting the turbine. So, these are the hydraulic parts that are used to control there is a hydraulic unit here to control the needle valve, right, needle valve for the signals coming from the control room. And the cross flow is a third type of, this is again impulse turbine, but simple construction. It is just a drum, right, it is just a drum and even locally can be fabricated. You can see from this opening, water comes and hit the this runner, right. The runner of this impulse turbine has a shape of a drum. One or several runner portions comprising of number of blades fixed between the two discs are fixed on the same axle. The cross flow turbines are relatively always installed with horizontal axis. So, it is a simple construction, even we can locally manufacture, right, locally manufacture it. Here are the advantages of it. You can see water coming from a rectangular opening is uniformly spread over the turbine, but you can make sectionalize it here, like here you can see you can sectionalize the opening. When there is less water, maybe a portion of the runner is hit, right. When there is medium water, two sections are hit, and when they have full range, you can have full water. So, accordingly your efficiency curve will be operating, right. Therefore, you can gain flat efficiency over wide range of part loads, right, part flow rates, whereas Francis does not have that. Francis have poor part load efficiencies, but you can see notice that this the peak efficiency of this cross flow turbines will not reach 90 level, maybe 80-85, in that range it will stop, right. The peak efficiency will be lower, but this is good because it can be even fabricated locally, not much higher technology is required. It is just you can see between two plates system of blades connected, right, and so it is just with steel you can even weld them and make it even a local turbine. For a village hydro, I think this might be a better option, because you do not want to spend lot of money. Then we come to the reaction turbines, second type of turbines, right. So, they are the runner is completely immersed in water 100% of the time, right. The most popular reaction turbine is the Francis turbine, we all have heard about. they are more suitable for medium head projects. For smaller heads, the propeller type Kaplan turbines, right, are more suited. Reaction turbines have relatively higher rotational speeds compared to impulse turbines, and therefore, it is easier to avoid a gearbox between the turbine and the generator. The fabrication of reactive turbines are relatively more complicated due to special shapes associated with the runner blades of them. Here you can see some Francis turbines, how they operate. You can see here this the spiral case going around. So, the water enters from this larger entry, and then from periphery they enter the turbine runner, right. So, there we have we do not have nozzles like needle valves, we have what we call the wicket gates, right, wicket gates, that side wicket gates which can open, right, and then there are guide vanes to guide the water flow and smoothly enter the turbine blade. The turbine blade operates on the principle of the Bernoulli principle, where you have one side longer, other side shorter. So, the flow comes here just like the air flow through a aeroplane. So, they have to leave the same way. Therefore, this side the speed is, they have to go faster, this side slower. Then there is a vacuum effect here, right, vacuum effect here. So, it will be lifted, right, or on this side there will be a force, right, there will be a force on this side. So, the blades have been shaped in this way, right, blades have been shaped in this way. So, when the flow goes on one side, there will be a force for the rotation, right, force for the rotation. So, the turbines of Francis turbine is enclosed in a spiral casing and the high pressure water is encircling it. Wicket gates release the high pressure water under controlled conditions to the turbine runner, while the guide vanes assist to enter the water to the correct angle. Water flowing through the complex shaped runner blades imparts the energy to the runner while exiting the turbine axially. So, finally, the water will be going down from the middle to the tail race, right. Here we can see the hydraulic control of the wicket gates. So, there are, you can see this will be rotating these brackets which are connected to the wicket gates inside. So, when you want to open and close, this will be going up and down, right, and the hydraulic pressure will come as per the signals coming from the water level controller or from the control system in the power plant, right. So, there is a that way that we can overcome this problem of part load poor efficiency of Francis turbines, right, Francis turbines, by employing, if you have a site, say you have a site where you want to have 1 megawatt or 1000 kilowatt plant, where Francis turbine is the suitable machine, but you have part load deficit, part load lot of time to operate part load, because if you look at your flow duration curve, right, Q percentage time or exceedance, right, it is like this, right. So, lot of time it will be in operating in low flow conditions, your rated flow may be here, right. There are lot of time machines are on part load, machines are on part loads. Therefore, you are operating here these efficiency points, right, which is a disadvantage, So, one solution is, instead of putting 1000 kilowatt machine, you put a say 700 kilowatt machine plus a 300 kilowatt machine, right. So, in the low flow conditions, you run the 300 kilowatt machine, which can run on almost full rated flow, because that small flow available will be the rated flow of this 300 kilowatt plant or the turbine, right. So, when you have medium flow, you use only the 700 kilowatt one. When you have high flow condition, somewhere here, you use both in this region you use 700 kilowatt, here you use 300 kilowatt, right. So, that your machines will operate always in the higher efficiency points, right, higher efficiency points. So, I visited one such plant in Germany. Here you can see I do not have both the machines here, this is the larger machine, there is a smaller machine here, right, from the same power plant. I could take, I do not have a picture with both clearly here, right. One machine is a large one and the other one is machine is a smaller one, right. So, this is feeding to a factory, right, this is feeding power to factory. So, they have used these different sizes because of the efficiency considerations, right, because of the efficiency consideration. So, one might ask then that you can't exchange spare parts etc., right, from one machine to the other, but these technologies are very proven. So, anything going wrong with the turbine is a very low chance. Even the generator technologies are very improved now. Therefore, unless you get a lightning strike or something and you destroy it due to your own mistakes, otherwise they are so reliable. No, you do not need to keep spare parts. It will happen very rarely. Right? These are very proven technologies. Of course, your relay systems and other things can fail, but the generator, turbine, etc., will not easily get damaged unless you make a mistake in your management or protection. Therefore, having two sizes is not a problem. Therefore, you can always advise, if some people are going for Francis turbines, consider having two different sizes, right, two different sizes. People prefer to put the same size. If you want to put this 1000 kilowatt, they might say then 500 into 2, right, and to go for similar capacity. That is the normal pattern. But in this hydropower business, we have to consider the efficiency curve, right, efficiency curve and suitably. And also then some might ask the question, how did you decide this, whether it is, here you have a picture, here you can see this is a smaller turbine, this is a bigger turbine, right. So, a smaller one runs when the flow is low, other one runs when the flow is high, right. So, one of the disadvantages of Francis turbine is that at part load the efficiency drops very fast. As a solution to this problem, the hydropower engineers sometimes opt to install one large Francis turbine together with a relatively smaller turbine at the same plant. Smaller turbine is used during the low flow conditions, and when medium flow is available, the larger unit is used. When the available flow rate is maximum, both turbines operate, right. So, you should be able to advise, right, anybody doing a Francis power plant, consider this option, right. Then how do you decide whether it should be 1000 kilowatt or 500 into 2 or 700 plus 300 or maybe 800 plus 200, right. So, we may have to decide, right. So, how do we do is, we do an energy generation calculation for each configuration, which we are going to see at a later discussion, right. We are interested in to see how many kilowatt hours or megawatt hours a plant can deliver, that we will discuss in a different program, right. But here you can see, so we must see what is the cost of the plant as well as how many million units kilowatt hours you can produce in this configuration, how many kilowatt hours, here how many kilowatt hours, here how many kilowatt hours, if you have the different configurations. So, because of the higher efficiency, highest efficiency one will produce the highest energy yield, right. And then you have to consider the cost also, because if you have one machine, your control system is only one control system, one synchronizing breaker, and the powerhouse will be smaller. But when you have two machines, little more space is required and the two control systems are required. So, some additional cost will be there. Then you must see whether the increase in the power generation is worth the additional cost over the long term, right. That financial analysis also you have to do, right, because otherwise you just for a few kilowatt hours, if you duplicate your everything, control systems and synchronizing and all the control panels, then it might be not that worth. So, after doing the calculations only you should decide which configuration and which capacities, right, which capacities to be used. Here this of course, this plant was feeding a hydropower turbine manufacturing plant. They have opted for, they have a hydropower opportunity in that area. So, they have their factory is fed by hydropower, right. They have a grid connection, but mostly they use their own generation, right, mostly they use their own generation. So, they have opted for the vertical axis, this is vertical axis configuration, right, in both unit side vertical axis configuration. Here is a Kaplan turbine. Kaplan turbine has a is a propeller, propeller, you have heard the word, I think. Propeller is the driving unit of a ship, right, a boat. I think you have seen the boats propellers, right. So, people take it out and go and fix it back, right, when they want to go. So, but in a ship it is permanently there. So, it is a propeller, when rotated pushes the ship forward, right. And so, this is the same technology. Now, the propeller is fixed and the water is pushed to it, then it begins to rotate, right, then it begins to rotate. But Kaplan is in a improvement of normal propeller, right, normal propeller, because in Kaplan the blades can be adjusted, blade angle can be adjusted to suit the better efficiency and to increase the efficiency for the given flow, right. So, the Kaplan is just a propeller turbine, where the blades can be adjusted by hydraulic means to maximize the efficiency, right. So, the design similar to a propeller of a ship, Kaplan turbines are very famous for low and ultra low head projects, Propeller type turbines are connected to the penstock, so that the axle of the turbines can come out of the pipe and can be connected to a generator, right. So, it is normally comes out of the pipe, the penstock. One marked advantage of Kaplan turbine is that the pitch of the blades of the turbine can be adjusted according to flow and thereby achieve higher efficiencies. So, here are some some parts of a typical project. You can see the same way wicket gates are there, guide vanes are there, the water comes and enter here, go through the blades and pass on to the other side, right, pass on to the other side, that is the normal way. And there while passing the same thing, same Bernoulli principle, shape of the blades will be having the similar pattern. So, that there is a longer path and a shorter path, thereby creating a vacuum and a force and thereby rotating it, right, rotating it. So, they are more suitable for low head projects and ultra low head projects. So, in one of our power plants we installed Kaplan turbines in a which is connected to a reservoir. So, because there was a irrigation outlet, as we discussed about some configurations earlier, there was a reservoir in Sri Lanka in middle part of the country, and where they issue water for irrigation work and for drinking purposes, and there is a height difference between the water issuing point and the water flow, about 30 meters. So, we discussed with the government authorities and got the approval and installed a 2.5 megawatt power plant there with two turbines, right. And so, they are Kaplan turbines. Now, they have been operating in last 10 years, no issues. Of course, we had one issue, as I told you earlier, that the penstock is FRP pipes, fiber reinforced plastic pipe. So, because of that vehicle movements, those got damaged by the pressure. So, we had to replace them. Other than that, about Kaplan turbine, there have been no issues. You know that your home water pump can also be used as a generator, a turbine, right. Home water pump, now when you rotate it, it will pump water up, right. But if you send water through it, it will rotate, right. So, if you want to, now if you have a in your home in a hilly area, if there is a waterway, you can easily put a pump, right, water pump as a generator and connect it to a induction generator or something very cheaply and generate some electricity. But the problem is their efficiency will be 50%, not that high, right, because they are not designed as hydropower turbines. But of course, as a practical means they can be very easily used as a practical machine to produce electricity, but they are not very efficient, right. By sending water in the reverse direction, centrifugal pumps can be used as turbines. However, one of the main disadvantages of these pump turbines is that the efficiencies are very low. It is very rare that pumps are used as turbines in building small hydropower plants. Main advantage of these turbines, they are available off the shelf, right, and pretty cheap as well. One problem with the hydropower turbines is these turbines you can't use any second hand turbines for a site, right. Second hand turbines you can't get. Why? There are no two identical, theoretically there cannot be two identical power plants in the world, right. In no power plant theoretically H and Q can be the same, right. H and Q cannot be the same in any two power plants. H is depends upon the height difference available, Q depends upon your catchment area and other things. So, it is hardly possible in two power plants both are the same. Therefore, these turbines have to be manufactured especially designed for this H and Q, right. So, you can't ask a hydropower turbine manufacturer, can you manufacture it in 2 months? He cannot. He has to first do a design and then manufacture it. So, they will take 6 to 9, 10 months for the manufacturing process, right, and then the generator also has to match the speed, right, number of poles, etc. So, it is a salient pole generator manufactured especially for this particular turbine speed, right. Therefore, they all take time to manufacture, right, they all take time to manufacture. Therefore, they are not available off the shelf, right. You can't go to a shop and buy turbines or generators for hydropower plants. So, they have to be specially designed and manufactured for the given site, right, for the given site. And also there are issues like that even though we say this efficiency, now manufacturer will say efficiency curve is this, right, but it is very difficult to measure this at the site, right. At site for the verification, how to measure these efficiencies is very complicated. Therefore, you can't now manufacturer will, even if he claims his machines are having 90% efficiency, to test it and confirm it at site is very difficult. Only possibility is if you are challenging him and asking him to prove it, he will say I will make a prototype and measure the efficiency in lab scale for the prototype. That is the best he can do, right. Measuring is not impossible, but it is a time consuming and lot of money is required for various parameters to be controlled. So, I have not seen any site where they confirm the efficiency curve by tests. It is a very lengthy process, right. It is a very lengthy process. So, not worth doing. So, that is why we have to take a good reputed manufacturer, right, get reputed manufacturer when you buy hydropower turbines. So, for all the turbines, so you use a turbine application chart for selection of the turbine to suit your head and flow rate, right. So, therefore, your particular plant can be any point in this chart. So, theoretically no two plants can be at the same point, right. Okay, accidentally it can happen, but theoretically we can't say any plant can be having the same location in this turbine selection chart. But you have the same multi options. If you are here, you have the option for going for Pelton or Francis, both, right. Then you can take a decision depending upon your flow. If your flow is like this, then your low flow conditions are less. Low flow conditions you can see, but mostly your flow is high flows, right. Then in that case you can use a even a Francis machine, right. But if it is like this, right, it is different, right. You have lot of part load conditions, therefore, you must consider a Pelton machine, right. Therefore, when you have multi machine options available, you must look at the shape of the flow duration curve, right, flow duration curve. Now, why the flow duration curve have these shapes? Now, when you look at the flow duration curve, you can tell the properties of your catchment area, right. When I look at, if somebody shows me this curve as his flow duration curve, I notice his catchment has less forest, right, and more rocky. What does it mean? The rain comes, water is quickly rushing into the river and going out, right. Therefore, high flows are more for a short time, right, and then water retention is not there. So, this is not good, therefore, this is not a good flow duration curve. This is a good one because water is retained in the forest or whatever the cover, vegetation cover, and slowly released over the years, then you can utilize it more, right. So, you can tell the properties of the catchment area by looking at the flow duration curve without visiting even the site. So, most of the surfaces are this one, most of the surfaces are rocky and less water retention, right. So, these are important things that when you are looking at the project. So, we discussed here the types of turbines used in small hydropower and special versions like turgo. Turgo is not used in large hydros, they are especially for small hydros, and Pelton is very much used in both small hydros as well as both Pelton and Francis are famous for the entire range from small hydros to large hydros. And so, the turbine selection should be carefully done, and when you are using multiple turbines, right, you can consider having different sizes if the part load efficiencies are poor of that turbine. So, that you can run the smaller version when the flows are low and the bigger version when the flows are medium, and both turbines when the high flow rates are available. I think we will stop there this discussion, and if there are any queries I can take up.
Hello sir.
Yes,
this
please.
is Supriya.
Yes, Supriya.
Sir, how these hydro turbines are different from the other turbines like gas turbines or other input turbines like nuclear turbines? Any change or?
Yeah, gas turbines. So, in the gas turbines you can see it is a hot in the hot air or heated air that passes through the turbine. You can see, and the construction wise there are large number of blades in a different shape, right, in a gas turbine what I have seen, and it is not a liquid that is flowing, it is a hot air. Hot means the heated air with energy goes through it, that after fuel burning or the gas burning goes to them and impart the energy into them. So, those blades are operating at very high temperatures. So, their construction, their materials, I am not an expert on gas turbines, but what I have seen is they operate in a completely different environment, and they also usually comes in two compartments, that is high pressure turbine and the low pressure turbine connected to a same shaft. So, first the hot air goes to the high pressure turbine, and then it passes go into a low pressure turbine, and their turbine blades are different, and thereby they try to maximize the energy usage, right. But in hydro turbines it is not like that. Hydro turbines, it is the fluid that goes through, of course, air can also be considered as a fluid in a way when it is flowing, but the hydro turbines, it is a physical impact by a impulse turbine or reaction by the fluid on the say Francis turbine, but a similar action is taking place in air flow in a gas turbine also, but the conditions are different. it is a heated hot chamber, this is a water chamber. But I think the operating principle may be the same as the Bernoulli principle in both cases.
Yes. Okay, sir.
Okay.
Thank you, sir.
Okay, thank you. Okay, we wind up there. Thank you.